Hello, Namaste. Welcome to this channel Chemistry Made Easy by Dr.ARM. Today we will see the next part of this topic, atomic structure, and today's point of our interest is discovery of subatomic particles. So what is meant by subatomic particles? These are the particles which are present in the nucleus and in the in the space around the nucleus. So these subatomic particles were discovered in different periods. So we will see the discoveries today here. The first, that is in 1896, A.H. Becquerel, who discovered the radioactivity phenomenon in case of uranium. So in that case it was a natural phenomenon and it was discovered by this Becquerel. Then in 1897 another scientist, J.J. Thomson, he showed that electrons are negatively charged and their charge to mass ratio is 1.76 into 10 raised to 11 coulombs per kilogram. Then in 1909 another scientist, R.A. Millikan, who measured the electronic charge, that is 1.16 to 10 raised to minus 19 coulombs. Therefore the electron is having the mass 9.11 into 10 raised to minus 31 kilogram, or in other words we can say, if we consider the mass of a proton, then the mass of electron is 1 upon 1836 the mass of the hydrogen atom. Means here hydrogen atom is nothing but a proton. So mass of this proton, if we take it, the mass of electron is 1 upon 1836th part. Then next discovery was made in 1911 by E. Rutherford. He established the nuclear model of the atom, and here he observed that, he interpreted that heavy mass is present at the center of the atom, that is called a nucleus, and there is large empty space surrounding the heavy mass of this nucleus. Another scientist in 1913, H.G.J. Moseley, who determined nuclear charge by X-ray emission, and he established atomic number as most fundamental property of an element or of the element rather than the atomic weight, because we have earlier studied that the periodic table that was prepared by Mendeleev and Mayer was based on by organizing the elements with increasing order of their atomic weights. But it was observed that the atomic weights are varying. It is not the same, or it is not a characteristic property of that particular element. But instead of that, Moseley said that the most fundamental property of the element is its atomic number rather than atomic weight. Then discoveries in atomic spectra showed that when the substance or when the atom is excited by electric discharge or heat, the atom showed emission of light of specific energy. Means when if we consider hydrogen, when hydrogen is heated or excited with electric discharge, it shows emission of characteristic emission of energy or characteristic emission of light with specific energy. In 1885, Balmer, who studied the hydrogen atom and the emissions taking place in this hydrogen atom after excitation, and energies of visible light emitted by the hydrogen, the energies which were emitted by hydrogen when it is excited by the electric discharge or heat, shows that the energy is given by this equation. E is equal to RH into 1 upon 2 square minus 1 upon NH square. Here RH is called a Rydberg constant. It has value for atom, hydrogen atom, that is 1.097 into 10 raised to 7 per meter. Then it is equal to 2.179 into 10 raised to minus 18 joules. Here NH is integer. It is NH is greater than 2. Here NH should be greater than 2. Then we can use this equation to find out energy of the hydrogen atom that was emitted when it is excited. Now we will see the energy in terms of various other properties or various other terms. So energy term can be explained in other terms such as wavelength or the wave number or frequency. So such units are also expressed or used in order to consider the energy term. So we have seen that energy is given by E is equal to h mu. E is equal to h mu. Here h is Planck's constant and mu is the frequency of the energy. Then here we will see that this term, that is energy, is also considered to be equivalent to another term, that is h into c upon lambda. Here nu is given by c upon lambda. Here c is the velocity of light, that is 2.9940 into 10 raised to 8. 2.998 into 10 raised to 8 meter per second, and lambda is the wavelength of that light. So here energy is given by this term. It is also given by h into nu bar, h into nu bar into c, or h into c into nu bar. Here nu bar is the wave number. So we can say E is equal to energy of the light emitted. H is Planck's constant, nu is frequency, and this c is velocity of light, lambda is the wavelength. Then nu bar is nu is frequency of the light and nu bar is wave number. So here we can have the energy obtained in different terms which are all equivalent, but these terms are used in different fields for our consideration of or as per our convenience. Then Balmer's equation was later on made more general, and the spectral lines in the UV and IR spectral region were discovered by replacing the 2 square and NH square. Here the NH was, here NH was replaced by, or which then 2 square is also replaced by, 2 square is replaced by NL, and NH is also replaced by any other number. We can replace 2 square is replaced by 2 square is not equal to, it is not equal to 2 square 2 raised to n, it is not 2 raised to n, but 2 square is replaced by NL, and NH is here NH and NL. Now we will see the relation between these two. Here NL is less than NH. Here what is meant by here? N. N is a principal quantum number. N is, we can take this or this N. Here N is equal to principal quantum number. Principal quantum number. So here NL is lower energy level and NH is, here it should be, NL should be less than NH. Here NH means H is or higher quantum number or higher level number. NL is, that is principal energy level, that is lower energy level. So in Rydberg's constant, when we replace E is considered as RH into 1 upon, instead of 2 square, if we use NL square minus 1 upon NH square. So this is based on the observations or spectral lines obtained in the spectral region of UV and IR. So here these quantum numbers, that is principal quantum number, principal quantum number is one more important discovery, which shows that it is the principal or main energy level of electrons present around the nucleus. So we will discuss all the quantum numbers and their features, etc. in another or next lecture. So till then, goodbye. We will stop here and we will continue our next discussion in the next lecture. So see you next time. Please subscribe to this channel and press like button and bell icon button. Thank you very much for watching this video. Thank you.